Write down the topic, properties of matter. Properties of matter. Question number 6. The approximate depth of an ocean is 2700 meter. Approximate depth of an ocean is 2700 meter. The compressibility of water is 4.54 into 10 to the power minus 10 into 10 to the power minus 10 Pascal inverse. And density of water is 10 to the power 3 kg per meter cube. 10 to the power 3 kg per meter cube. What fractional compression of water will be obtained? What fractional compression of water will be obtained at the bottom of the ocean? Obtained at the bottom of the ocean. From the definition of bulk modulus, you can find the formula to solve this problem. Bulk modulus B, P by dV by V. I am ignoring the minus sign. So bulk modulus B equal to pressure by, pressure means volume stress, and delta V by V means volume strain. So what we have to calculate? So B can be written as 1 by K, where K is considered as the compressibility factor. Compressibility factor is inverse of the bulk modulus. So from this we can write it is equal to P by dV by V. So you can write dV by V equal to K times P. Compressibility factor is given. You can calculate the value of P by using the formula rho GH. Okay, so we can write here K into H rho G, because depth of the water is given in the sea, rho is given, you have to use G to find pressure. Pressure into compressibility factor will give you the fractional change in volume, that is volume strain, that is required in the problem. Okay, so it is coming nearly 1.2 into 10 to the power minus 2. And what will be its unit? What will be the unit? No unit. Why? Tell me why no unit? Because it is the fractional change, means change in volume by original volume. So it has no unit. Correct. Question number 9. the breaking stress for a copper wire is 2.2 into 10 to the power 8 Newton per meter square. The breaking stress for a copper wire is 2.2 into 10 to the power 8 Newton per meter square. The maximum length of copper wire which when suspended vertically for which the wire will not break. The maximum length of the copper wire which when suspended vertically for which the wire will not break under its own weight will be density of the copper is 8.8 into 10 to the power 3 kg per meter cube. 8.8 into 10 to the power 3 kg per meter cube. Option A 25,000 meter. 25,000 meter. Option B 2500 meter. Option C 250 meter. Option D 25 meter. So it will come L equal to 2.2 into 10 to the power 8 divided by 8.8 into 10 to the power 4. So it is coming 1 by 4 into 10 to the power 4. That means 250. 2,500. One more. And 4 is there. 2500 meter. Option B. Two wires are made of the same material. Two wires are made of the same material and have the same volume. The first wire has the cross-sectional area capital A and the second wire has cross-sectional area 3A. Second wire has cross-sectional area 3A. If the length of the first wire is increased by delta L, if the length of the first wire is increased by delta L on applying a force capital F, on applying a force capital F, comma, how much force is needed to stretch the second wire by the same amount? How much force is needed to stretch? What? Oh, two wires are made of the same material and have the same volume. Two wires are made of the same material and have the same volume. The first wire has cross-sectional area capital A and second wire has the cross sectional area 3A. Okay. If the length of the first wire is increased, if the length of the first wire is increased by delta L on applying a force capital F, on applying a force capital F, comma, how much force is needed to stretch the second wire by the same amount. How much force is needed to stretch the second wire by the same amount? Option A 4F, option B 6F, option C 9F, option D F. This is the formula for Young's modulus. Y equal to F by A divided by delta L by L, means longitudinal stress by longitudinal strain. Now from this I can write F equal to YA delta L by L, F equal to YA delta L by L. For anywhere I can consider a cylindrical shape, and if the volume of this wire is V, length is L and area of cross section is A, then I can write V equal to AL. Okay, V equal to AL. So replace L here. L should be replaced by this. So we know that L will become V by capital A. Just substitute here. L will be V by capital A. Then it becomes F equal to Y A square delta L by V. Y A square delta L by V. Okay. Now, for both the wires, increase in length should be same. So delta L are equal. Volume of the wires are equal. Young's modulus are equal because they are of same material. So in that case, F is directly proportional to A square. Okay. So we can write F1 by F2 should be equal to A1 square by A2 square. Now F1 is given F, then we have to find force for the second wire which can produce the same elongation. So this is equal to A1 square. A2 will be 3 times A1. So F2 will become 9F. Length is given, so convert it to volume because it is given that volume of the two wires are same. Okay, then delta L constant for both the wires, Y constant for both the wires, V constant for both the wires. So in that situation, F is directly proportional to area square, area of cross section square. So from that I can write F1 by F2 equal to A1 square by A2 square. Now F1 is given F, so what is F2? Area of cross section is 3 times for the second wire than the first wire. Is it clear to everyone? Write down question number 26. A soap bubble of radius small r, a soap bubble of radius small r is blown up to form a bubble of radius 2r. A soap bubble of radius small r is blown up to form a bubble of radius 2r under isothermal condition. Under isothermal condition. If T is the surface tension of soap solution, if T is the surface tension of the soap solution, the energy spent in blowing is 3 pi small t, 3 pi capital T r square, option A, 3 pi capital T r square, option B, 6 pi capital T r square, option C, 12 pi capital T r square, option D, 24 pi capital T r square. See, work done is the work done required to increase the bubble surface area. Blow the air into the bubble means surface tension into increase in area. Okay, now what is the total increase in area? Most of you will think that this one, 4 pi 2r whole square minus 4 pi r square, but this is not the total increase in surface area. You have to multiply it with a 2, because inside the bubble there is a free surface exposed to air, outside the bubble there is another free surface exposed to air. So increase in area is on both sides of the soap bubble. So that's why you have to multiply with this extra 2. Otherwise the answer will not come. If it is droplet, then only this one is the increase in the surface. But soap bubble means there is a soap film, inside there is air, outside there is air. So whenever it increases, two sides area will increase. So that's why a 2 is required. So now it will be 4 pi into 2r square. 2r square means 4. 4 into 4, 16 pi r square. It is 4 pi r square means 12 pi r square multiplied by 2. That is 24 pi t r square. That is the answer. Okay. This is the Jurin's law for capillary rise. 2s cos theta by rho g. Okay. So from that you can solve. I can write here that both capillary has the same radius. So RH1 by RH2 for the second capillary equal to 2s1 cos theta 1 by rho 1 G divided by second one, so it will be rho 2 G by 2s2 cos theta 2. So this R will cancel, 2 will cancel, G will cancel. Okay, so now it is given that H1 equal to 6 centimeter. You have to find H2. Now S1 by S2, S1 is given, S1 is 70, S2 is 140. Cos theta 1, that is cos 0, cos 0 is 1, divided by cos theta 2, cos 60, that is 1 by 2. So 1 divided by 1 by 2, so it will become 2 into rho 2 by rho 1, that is given relative density 2. Okay, so H2 will be 6 by 2, that is 3 centimeter. A cylindrical vessel of radius r containing a liquid is rotating about a vertical axis through the center of circular base, If the vessel is rotating with angular velocity omega, then what is the difference of the heights of liquid? What is the difference of the heights of liquid at the center of the vessel and the edge? Option A, R omega by 2g. Option A, R omega by 2g. Option B, R square omega square by 2g. Option C, root over of 2gr omega, entire thing inside root over of 2gr omega. Option D, omega square divided by 2gr square, omega square divided by 2gr square. HA equal to HB, that is from the reference level. Okay, now according to Bernoulli's theorem, I can write at point A pressure PA, then kinetic energy density half rho VA square plus rho G HA, that will be equal to PB plus half rho VB square plus rho G HB, right? Rho G HB. Now from these two I can write rho G HA equal to rho G HB, because HA equal to HB. Okay, now let us consider when it is rotating, the top and this bottom, they are at a difference of height h. When it is rotating, then bottom of the water and top of the water are at a distance h. Okay. Now, at which point pressure is more? At B or A? Due to the liquid? No. This height is h. This height is almost 0. So that is the pressure due to the liquid itself is different at point A and B. If it is static liquid, then pressure at all point remain same at the same horizontal level. Since it is not static liquid, so the pressure will be different. From the bottom and from the edge to the center, there is a pressure difference. So at this point and at this point there is a pressure difference. So I can write that PB minus PA, that is equal to half rho into VA square minus VB square. Okay, PB minus PA equal to half rho into VA square minus VB square. Okay. Now, this one will be H rho G. This one will be half rho, and VA is zero, because center means almost not rotating. So VA will be 0. And what is VB? R omega. Okay. Neglect that minus sign, because minus sign is for measuring from this here to here, only the coordinate convention. You can also put that this one is minus sign, because taking the coordinate convention from opposite side. Okay, so in that case it will be H rho G, because whenever we measure at a depth, pressure at a depth, we measure it from the top level to the bottom. So that's why here it is taken from bottom to top, that's why I put this minus sign. So H rho G will be half rho R square omega square. So rho will cancel. So from that you can find the value of H. That is R square omega square by 2G. That is the answer. Because at the center liquid is almost not rotating. So that's why at the center speed is 0. And at the edge it is rotating with its angular speed omega. So angular linear speed will be R square omega, R omega. So its square will be R square omega square, and you can substitute. A liquid of density rho naught, a liquid of density rho naught is filled in a white tank, is filled in a white tank to a height small h, to a height small h, full stop. A solid rod of length capital L, a solid rod of length capital L, cross sectional area capital A, cross sectional area capital A, and density rho is suspended freely in the tank, is suspended freely in the tank. The lower end of the rod touches the base of the tank lower end of the rod touches the base of the tank and the height of the water level H equal to height of the water level H equal to L by N, where N greater than 1. Means there is a relation between length of the rod and height of the liquid level. It is given as H equal to L by N. Then the angle of inclination of the rod, with the horizontal in equilibrium, angle of inclination of the rod with the horizontal in equilibrium will be options: sin inverse 1 by n root over of rho naught by rho. Option B, sin inverse 1 by n root over of rho by rho naught. Option C, sin inverse n into root over of rho naught by rho. D, sin inverse root over of rho naught by rho. Equilibrium of a rigid body. Equilibrium of a rigid body means statics. What is the condition for equilibrium of a rigid body? Net force should be 0 and net torque should be 0. So consider a point of the rod or any point and calculate the net torque about that point and equate it with 0. Then we can find a relation between capital L and small l. Small l means the length of the rod that is immersed inside the liquid. Okay. So from that you can determine the angle. Net torque should be 0. Then there will be rotational equilibrium. See, this one is the diagram. Consider this one is the rod. Okay. So a portion of the rod is outside. Now center of mass of the rod lies at its midpoint. So through that the weight will act downward, and center of buoyancy act through the midpoint of this immersed length, through that upward. So center of buoyancy means the midpoint of this length, and center of mass means midpoint of the entire length of the rod. So see, center of buoyancy and center of mass or center of gravity are not the same point. Okay. Now about any of the point in the problem, you have to balance the torque. Let us consider the best option is this point. Consider this point as P and calculate the torque of these two forces about P and make it equal to 0. Why I am taking this point? Because this force I can calculate, this force I can calculate, but at this point there is a normal reaction force, and even that normal reaction is not exactly perpendicular. It has two components. So if I write Nx, Ny and all these things, normal reactions component, contact forces components, then I have to write the two force equations also. That means vertical equilibrium and horizontal equilibrium for force. And from that I have to find Nx and Ny. So it is better to calculate torque about this point, because then the normal reaction, whatever be its direction, torque through this point will be 0. So to bypass that normal reaction calculation, I consider the equilibrium about this point. You can also consider this point or any other arbitrary point. But in that case calculation will be more difficult, because if you choose suppose this point, okay fine, that is also possible. But for that this force and normal reactions torque you have to calculate. And you don't know normal reaction in this case. That's why for translational equilibrium you have two equations, that all x component of forces will be 0 and all y component of forces will be 0. From that, by solving, you have to find normal reactions component and then solve the problem. So that's why better the normal reaction is unknown to us and we will not go for calculation of the normal reaction. Rather I will take this point for the calculation of the torque, because in that case the normal reactions torque will be automatically 0 and it will not come in the equation. So you will have to calculate the torque for B and W about point P and equate them. Let us consider the entire length of the rod is given L, and from that consider this length, say P, this is Q. PQ length is considered as L. This is the perpendicular, so this is the height of the water, that is considered as H. Suppose R, this point is R, H, and P2, this say S. PS is the total length, that is capital L. QR is the height of the liquid, that is H, and this H is given L by N. L by N, H is given. PQ length is given small l, is considered as small l. We considered that is not mentioned in the problem, that PS length is the length of the rod, that is considered as capital L. QR is the height of the liquid, that is considered as H. Then consider that this angle is theta. You have to find that theta. First calculate the torque of B and W about point P and equate it to 0. Then you will get a relation between small l and capital L. We require that equation. See, this point P about which we are going to take the torque. Now tell me, for buoyant force about this point, torque will be clockwise or anti-clockwise? This point is fixed. Now consider the direction of the buoyant force and tell me buoyant force about this point will produce a clockwise torque or anti-clockwise torque? Anti-clockwise torque. Why? This is the rigid rod. This is the buoyant force upward. So it will rotate it. See, anti-clockwise sense. So buoyant force, since it is pulling it up, so it will produce an anti-clockwise torque about this point. Anti-clockwise torque is taken as positive. Okay. So I will write magnitude of buoyant force into, later I will put the buoyant force exact expression, magnitude of buoyant force, suppose B, then perpendicular distance of the line of action of the force from this point P about which the torque is taken, means this distance. Now from this point up to this, what is the length? Small l, because buoyant force is passing through center of buoyancy, which is the midpoint of the length PQ. Okay, so PQ's midpoint will be this one, so it will be L by 2. Then this part will become perpendicular distance, that is L by 2 cos theta. So I write B L by 2 cos theta. That is the torque produced by buoyant force about point P. Clear? Because how to calculate torque about a point? This is the direction of the force. So this is the line of action of the force. From this point you have to drop a perpendicular over the line of action of the force and take that distance. Okay, this is the rules for calculating torque. The magnitude of the force multiplied by the perpendicular distance of the line of action of the force from the axis of rotation. So that is the perpendicular distance. Now for weight, torque will be W into, weight is passing through center of gravity or center of mass. That means half of the length of capital L. Okay, so capital L is P2S, so it is passing through this point. Now what is the perpendicular distance? P2 R, that is capital L by 2 cos theta. Similarly, because this much part is L by capital L by 2, I will not write that because it will be too clumsy. Then its perpendicular distance will, from this line of action of W will be L by 2, capital L by 2 cos theta. With a minus sign, because this W will produce a clockwise torque. See, this is the rod, W is pulling it down, so it produces a clockwise torque. So this should be equal to, this should be 0. Okay, clear? Now put the expression for buoyancy for this rod. How much length of the rod is immersed? Small l. So buoyancy will be volume immersed, that is A into small l. Area of cross section we consider capital A. So A into L will be the volume of this rod which is immersed in the liquid, AL, into density of the liquid. What is the density of the liquid? Rho naught into L by 2 cos theta. this will be equal to weight. Weight means mass into gravity for the entire rod. Mass into gravity for the entire rod. There is one more G for the buoyancy. Volume into density into acceleration due to gravity is the buoyant force into L by 2 cos theta. Okay. We write buoyancy equal to V sigma G. So here V is A into small l, which portion is immersed. Rho naught is the density of the liquid and G is the acceleration due to gravity. So this part is the buoyant force. Remaining L by 2 cos theta comes for the torque calculation. Now, so this should be equal to W. W means mass of the rod. Mass of the rod means volume of the rod into density of the rod. So volume of the rod is A into capital L. Volume of the rod is the entire rod. So it is A into capital L into density of the rod rho, perpendicular distance, that is L by 2 cos theta. So I write B L by 2 cos theta. That is the buoyant torque produced by buoyant force about point P. Clear? Because how to calculate torque about a point? This is the direction of the force. So this is the line of action of the force. From this point you have to drop a perpendicular over the line of action of the force and take that distance. Okay, this is the rules for calculating torque. The magnitude of the force multiplied by the perpendicular distance of the line of action of the force from the axis of rotation. So that is the perpendicular distance. Now, for weight, torque will be W into weight is passing through center of gravity or center of mass. That means half of the length of capital L. Okay. So capital L is P2S. So it is passing through this point. Now what is the perpendicular distance? P to R. That is capital L by 2 cos theta. Similarly, because this much part is L by capital L by 2. I will not write that because it will be too clumsy. Then its perpendicular distance will from this line of action of W will be L by 2, capital L by 2 cos theta. With a minus sign, because this W will produce a clockwise torque. See, this is the rod, W is pulling it down. So it produces a clockwise torque. So this should be equal to, this should be 0. Okay. Clear? Now, put the expression for buoyancy for this rod. How much length of the rod is immersed? Small l. So buoyancy will be volume immersed, that is A into small l. Area of cross section we consider capital A. So A into L will be the volume of this rod which is immersed in the liquid, AL, into density of the liquid. What is the density of the liquid? Rho naught into L by 2 cos theta. This will be equal to weight. Weight means mass into gravity for the entire rod. Mass into gravity for the entire rod. There is one more G for the buoyancy. Volume into density into acceleration due to gravity is the buoyant force into L by 2 cos theta. Okay. We write buoyancy equal to V sigma G. So here V is A into small l, which portion is immersed. Rho naught is the density of the liquid and G is the acceleration due to gravity. So this part is the buoyant force. Remaining L by 2 cos theta comes for the torque calculation. Now, so this should be equal to W. W means mass of the rod. Mass of the rod means volume of the rod into density of the rod. So volume of the rod is A into capital L. Volume of the rod is the entire rod. So it is A into capital L into density of the rod rho into G into L by 2 cos theta. Now many things will cancel. A cancels, cos theta cancelled, G cancelled. Okay, this 2 will also cancel. So it is coming that L square into rho naught equal to capital L square into rho. Okay, L square, small l square rho naught equal to capital L square rho. Clear? Now from this we can write L by L means capital L by small l. It is coming root over of rho naught by rho. Two equal drops of water are falling through air with constant velocity v. If the drop combines together, what will be their new velocity? Option is there, but I will not tell the option. Calculate. Means it will be in terms of V, but what will be that? How a water drop can fall under gravity with constant velocity? The problem mentions that it is falling with a constant velocity. How under the gravity a drop can fall with constant velocity? Because constant gravity will produce constant acceleration. Then how constant velocity can come? How under gravity constant velocity can come for a liquid drop? Just tell me this one. Gravity is an accelerating agent, so everything falling under gravity is accelerating. So how a liquid drop can fall under gravity with constant velocity? Gravity is not the only agent through which the liquid drop is falling. It is falling through atmosphere. Means viscous force will be there, and when the terminal velocity is achieved, then the velocity will become constant. So that is the case when this velocity v is given, it is actually the terminal velocity of the water drop. Then you have already studied one equation for calculating terminal velocity of spherical bodies. You have already studied that. Because when terminal velocity is achieved, then weight will be balanced by buoyant force of air plus viscous force. because viscous force is upward, buoyant force is upward, weight is downward. Terminal velocity means net force 0. Net force 0 means weight is equal to buoyant force plus viscous force, and that viscous force is calculated from Stokes' law, 6 pi eta RV, and equating that you will get a relation between terminal velocity in terms of the other quantities, that Vt equal to 2 by 9 eta r square g into rho minus sigma, where rho is the density of the liquid and sigma is the density of the air through which it is falling. Sigma means density of the medium and rho means density of the object which is falling. So here water drop and air density. So using this equation you have to solve the problem.
2 by 3 factor to the power 2 by 3 please.
See, when the drops combine, the radius changes, and this is the formula between terminal velocity and radius. So with that new radius, the new terminal velocity will come. Okay, see. When the two drops combines, the total volume remain constant. Okay, so for the bigger drop I consider 4/3 pi capital R cube, and for small drops it will be 4/3 pi small r cube into 2. So two smaller drops volume will be equal to the volume of the bigger drop. From that 4/3 pi will be cancelled, then you can write r equal to 2 to the power 1/3 into small r. Okay, r equal to 2 to the power 1/3 into small r. Now from this relation you find that this terminal velocity v is directly proportional to r square. So for two cases I can write capital V by small v equal to capital R square by small r square. Capital V by small v equal to capital R square by small r square. Then capital V by small v, this is capital R square, means 2 to the power 2/3 small r square by small r square. So V will be 2 to the power 2/3 small v. So for the bigger drop, the velocity will be 2 to the power 2/3 into velocity of the smaller drop. Volume remains same for two droplets. When combined to form a single drop, the volume remains same. So from that you have to find the relation between radiuses of the small drops and bigger drops, and then using this terminal velocity equation you can solve the problem. Because eta, rho, sigma, g all remain constant. So speed of the drops is directly, terminal velocity of the drops is directly proportional to its radius square. Now new radius will be 2 to the power 1/3. So it will be 2 to the power 1/3 r square